So today we start discussion of water, water as a solvent, osmolality, acids, bases, and buffers. So approximately 60% of our body is water, and water is distributed between intracellular and extracellular compartments. Water is a major solvent of life. It bathes our cells, dissolves and transports compounds in the blood, provides medium for movement of molecules into and throughout cellular compartments, separates charged molecules, dissipates heat, and participates in chemical reactions. So our body maintains a nearly constant amount of water. That's about 50 to 60% of our body weight. And total body water, that composition you need to know. And that read and learn, please, this figure. So now let's go on discussion of water. Osmolality and water movement. So water is distributed between the different fluid compartments according to concentration of solutes or osmolality of each compartment. So here is shown how to calculate osmolality of 0.9% sodium chloride solution. So an osmolality of the solution is 310 milliosmomoles per kilogram of water. So because osmolality is not, because sodium chloride is not completely dissociated, so real osmolality of the solution is slightly low and equals to 290 milliosmomoles per kilogram water. And this is osmolality of blood plasma. Because of this, we can intravenously give the solution without problem, because this solution is isotonic solution. Now let's discuss acids, bases, and buffers. First of all, you need to know definition. What's the acid? Acid is any chemical substance that can donate a hydrogen ion. And the base is any chemical substance that can accept a hydrogen ion. So acids release hydrogen ions and bases accept hydrogen ions. So now what the pH? pH is the minus logarithm of power 10 of hydrogen ion concentration. When I ask students what the pH, they always answer me that pH is a hydrogen ion concentration. No, that is minus logarithm of power 10 of hydrogen ion concentration. Now, you know that water is slightly dissociated. You should know this from organic chemistry, and the degree of ionization of water at equilibrium is small. At 25 degrees Celsius, only about 2 of every 1 power 10 molecules, this is power, yeah, that is typing problem, in pure water are ionized at any instance. Here you see dissociation of water and the dissociation constant. So equilibrium constant for the reversible ionization of water is this. In pure water at 25 degrees Celsius, the concentration of water is 55.5 moles. So grams of, also what is this? That is grams of water in 1 liter divided by its gram molecule weight. So it shows molar concentration of water. This square bracket means molar concentration. So we know that molar concentration of water, that is 55.5 moles. So And this is essentially constant in relation of very low concentration of hydrogen and OH ions. Now we know molar concentration, and we can substitute 55.5 moles in equilibrium constant expression to yield. And now we have this equation. Now, rearranging this becomes, and this is known as ion product of water, or KW. So KW means ion product of water. And we can write now this way. Am I right? So you think, and KW is 1 times 10 power minus 14 mole square. So don't forget that this constant is determined by electrical conductivity measurements of pure water, and is equal to 1.8 times 10 power minus 16 moles at 25 degrees Celsius. So substituting this, we'll get that ion product is water is this 1 times 10 power minus 14 moles square. Thus the product in aqueous solution at 25 degrees Celsius always equals this 1 times 10 power minus 14 mole square, when there are exactly equal concentrations of hydrogen ions and OH ions as in pure water. The solution is said to be a neutral pH. So at this pH, the concentrations of hydrogen and OH can be calculated from the ion product of water, as here is shown. And solving this for hydrogen ions, we can calculate concentration of hydrogen ion. So molar concentration of hydrogen ion equals to 10 power minus 7 moles. Now here you see this table which shows pH and different concentrations of hydrogen ions. And term pH is defined by this expression. Now we know this. Now you need to know pH of different fluids of our body. Blood plasma pH, which equals to 7.4. This is pH of arterial blood. Venous blood pH is slightly lower and equals to 7.35. Interstitial fluid pH, cytosol pH, so which is near 7, lysosomal matrix, which is below 5, gastric juice pH, which is 1.5 to maximum 3, pancreatic juice 7.8 to 8, saliva that is 6.4 to 7, and urine pH varies from 5 to 8. So almost every biological process is pH dependent, and a small change in pH produces as large changes in the rate of the processes. Because of this, cells and organisms maintain a specific and constant cytosolic pH, usually near 7, keeping biomolecules in their optimal ionic state. So we can say that in multicellular organism, pH of extracellular fluids is also tightly regulated. So why? Because there are molecules sensitive to pH, and these molecules are enzymes, receptors, ion channels, pumps, membrane transporters, proteins. what are mechanisms that regulating pH of multicellular organisms? These are three major systems. So I want to discuss these systems, but before we start discussion of these systems, you need to know two major terms. Term alkalosis, which refers to the excessive removal of hydrogen ions from body fluids, and acidosis, which refers to the excess addition of hydrogen ions. Now, there are three major systems regulating our body pH. First, that is chemical acid-base buffering. This buffering system acts immediately, but it's not a powerful system. Second, that is respiratory center, which regulates the removal of carbon dioxide as a gas in the expired air from the plasma, and therefore regulates bicarbonate ion concentration. This response occurs in minutes. That is more powerful than acid-base buffering. Third system is the kidneys. Kidneys excrete either acid or alkaline urine, regulating our body pH. This is very powerful regulatory system, but needs time, hours, and even days. Now our purpose is to discuss this system, acid-base buffering system. So today now we are going to discuss this acid-base buffering system and bicarbonate buffering system, which acts with respiratory center and regulates our body pH. Now, first of all, what the buffer? So that is any substance which reversibly consumes or releases hydrogen ions. Buffers minimize or attenuate changes in pH by consuming or adding hydrogen ion in such a way to minimize discrete changes. Now, buffers are aqueous systems that tend to resist changes in pH. One small amount of hydrogen or OH are added. So, and this system, aqueous system, contains a weak acid and its conjugate base. Weak acid, which acts as a proton donor, and conjugate base, which acts as a proton acceptor. Buffers consist of a weak acid and its conjugate base. Weak acids are dissociated partially. As here you see dissociation of weak acid, and weak acid is dissociated into weak conjugate base. This is A charge minus, and plus hydrogen ions. Dissociation constant equals to, here is shown, dissociation constant for this weak acid. Now, here you see this dissociation constant of weak acid, and now let's solve these for hydrogen ions, this, yes? Then take negative logarithm of both sides. That negative logarithm of hydrogen ion of power 10 and that negative logarithm of Ka and this ratio. Now substitute pH for minus logarithm of hydrogen ion concentrations and pKa for minus logarithm of Ka, and we'll get this equation. Now let's invert this minus logarithm, yes, and write equation this way. And this equation is known as Henderson-Hasselbalch equation. What's the application of Henderson-Hasselbalch equation? So why do we need this? So you see then when, so buffer solution contains weak acid and conjugate base. Buffer solution acts as a buffer and maintains pH of solution when a small amount of acid or base are added, when it contains both components, and acts and shows maximum capacity when weak acid concentration equals to base concentration, or when this ratio is 1. And when this ratio is 1, pH equals to pKa. So maximum capacity, so each buffer solution shows maximum buffering capacity when pH solution equals to pKa. Now let's draw a graph which shows dependence of pH of weak acid on OH equivalence, OH added. Yes, equivalence, OH added equivalence. So, and let's discuss this in the case of acetic acid. You know that acetic acid is a weak acid. And here you see this graph, and this midpoint, here you see midpoint, is expressed as pKa in Henderson-Hasselbalch equation. So, defined as the pH at which 50% of weak acid is dissociated. As you add more OH ions and move to the right on the curve, more of conjugate acid molecules dissociate, yes, to generate hydrogen ions, which combine with added OH ions to form water. Now, if you add hydrogen ions to the buffer and move to the left of the midpoint, conjugate base molecules combine with added hydrogen ions to form acetic form of weak acid. And there is almost no fall in pH. You see that this solution shows maximum buffering capacity in this region. Yes? So, and this region is known as buffering region, and this equals to pKa plus minus 1. So buffering region for acetic acid is from 3.76 to 5.76 because pKa equals to 4.76. Now I have a question. Can this solution act as a buffer in this cell? No, because pH of the cell is near neutral area, and at pH 7 it cannot act as a buffer. This is buffering region for the acetic acid. So this acid cannot act as a buffer in this cell. Now I want to show a titration curves of different pairs, weak acid and conjugate base pairs, which is that for acetic acid and for these pairs, phosphate pairs, and ammonia, yes, and you see that buffering region, so pKa for this pair is 6.86, so pKa for dissociation of this phosphate anion is 6.86, and this is buffering region for this solution, so it can act as a buffer. So buffering capacity depends on pH of the solution, and at the same depends on the concentration of weak acid and conjugate base. So more concentrated buffer are more effective simply because they contain a greater total number of buffer molecules per unit volume, then can dissociate or recombine with hydrogen ions. So, and now let's, okay. Now let's discuss the chemical acid-base buffering. So these are phosphate buffer, bicarbonate buffer system, and proteins that can that play very important role in our cells. So now this presentation contains all the buffering systems acting inside these cells, and last slide contains information that is necessary for preparing this material and contains questions. Please answer the questions at the end of the lesson. Okay, thank you very much.